Okay, good morning to everybody. Now, let us begin here. This is post-graduation second year MSc Mathematics. Paper is sixth paper, functional analysis. Okay, nice to meet you. Once again, heartily welcome to behalf of the online session. Now, this is the first class of online session, functional analysis, that is the paper sixth. Okay, now, before that, we have learned in previous classes or previous session here, what is the functional analysis? Now, first of all, what is the analyzation? Analysis means analyzation. It can be divided into number of branches. Here the analyzation means some of the elements must be arranged on the boundary section throughout the line and linear spaces of the part. Okay. Now, here the concept is analyzation throughout the real numbers. Some of the real numbers must be arranged in the systematical order, and hence the following axioms are satisfied. Now, that is the field axiom, order axiom, and completeness axiom. So, that is called the real number system. It referred as RNS. That is called a real number system. Now, hence the real number system means some of the real numbers must be arranged as the following axioms are satisfied. What are the axioms? So, sometimes axioms may be referred as properties, postulates, conditions, laws. Okay. Now, enter the concept of analyzation and algebra. Here the algebra and analysis, one of the interlinked part. Now, here the suppose algebra we have taken the algebra. So, some of the binary elements must be arranged. Okay. So, with respect to the binary axioms. Okay. Here the binary axioms is ordinary addition, and ordinary operations are addition, subtraction, multiplication, division. These are all ordinary operations. Okay. So, that operations is also here the first of all, here RNS means real number system. Now, first of all, real number system means real number system. Okay, that is the full form. Here, what is the RNS? First of all, field axiom. Field already introduced in the UC level, that is called modern algebra. In sometimes that is also called abstract algebra. Okay. Now, already we have the introduced the concept of what is the group from the beginning of modern algebra. That is the group and number theories concept. Okay. Now, according to the number theory, we have learned what is the group. Okay. And abelian group, ring, subring, field, subfield. Okay. That entire the concept of modern algebra. And at the same time, linear algebra is there. One of the algebra is linear algebra. Okay. In that linear algebra, so that is also entire the concept must be surrounded the part of linear spaces. That is the three-dimensional space of the part. Here the x-axis, y-axis, and z-axis. Now, throughout the space, now here each and every space must be represented as one of the line. Okay, one of the axis is there. So, that axis here represent the axis means that is also one of the line. A line consists at least 2 points. So that is also one of the directed line segment. So x be the one of the directed line segment, and y axis be the one of the directed line segment, and z axis is also one of the directed line segment. Now these three axes must be represented as the entire the space of the part. So throughout the space, inner space of the elements are called vectors. Now, those vectors are called objects, and outside of the elements are called field of the elements, and those elements are called scalars. So, throughout the vectors and scalars must be represented throughout the dimension. Now, we have to introduce what is the vector space. So, from the beginning of functional analysis, here the analyzation concept is real numbers and complex numbers. So, some of the real numbers must be arranged in the systematical order, as in the systematical order means. So, those real numbers must be arranged in the enter the space of the part, that is called real linear space. So, that is also represented as you have learned in the one of the definition is linear space or vector space is there. So, already we have learned in real analysis is there. So enter the real analysis means that is one of the analyzation of the concept. Now it was observed from real number system, real sequences and infinite series, and at the same time limits and continuity and differentiability, integrability. So that integrability is also introduced from the linear space throughout the dimension. So that is called the integrability is means throughout the real line. Okay. So that is one of the real analysis. At the same time, that is also one of the paper of under UG level is there, and at the same time, the theory was developed in the previous paper is there. That is the paper 2 in the first year. That is the real analysis. So throughout the complex numbers must be analyzed here. That is one of the analysis. Okay. Now, and at the same time, in the first year, MSc Mathematics first year papers, real number, real analysis, that is the paper 2. And at the same time, paper 5 is the topology. That is also functional analysis. Now, same that theory is also developed from the both combinations of algebra and analysis and interlinked of the parts. And according to that paper is also discrete of the part. That is the DMS. Okay. That is the third paper in the first year. But at the same time, throughout the topology is also continuing of a part of the paper is functional analysis is there. Okay. Now, throughout the functions, before that, what is according to the real linear space. So, some of the field elements is called, some of the field elements are real numbers. So, that vector space, what is the vector space? And before the learning of the functional analysis, first of all, we must introducing the definition of real linear space or vector space is there. What is the vector space? Here, any one of the binary operation, star be any one of the operation, V cross V to V, be any non-empty set of a mapping is said to be a vector space. Okay. Now, first of all, so we must arrange the one of the binary mapping is there. And throughout the binary mapping, be any non-empty set. So that non-empty set of the elements, inner space of the elements are called, that is called objects. So those elements are called vectors, and outside of the elements are called scalars. Okay. Now, here the first of all, here V under V be any non-empty set, V not equal to pi. Here pi be any pi be a empty set is there. Not equal to pi means non-empty set. Okay, students, listen carefully. Now, for enter the concept must be introducing of the from the definition of linear space. So already that linear space we have learned in the real analysis paper is there. Once again, I have to repeat here, without the definition, we can't explain the normal linear space. So first of all, what is the linear space is there? Okay. Here, yes, a star or circle, whatever be any one of the binary operation or binary operation, binary composition, whatever it is. Okay. Now, here binary composition means star be any one of the binary operation. That is the universal operations. So, universal operations are circle and star. Here we are taking the one of the star be the one of the binary operation. Star defined from V cross V to V be any non-empty set of a mapping is said to be a vector space. Now, if the following conditions are satisfied, okay, please stay on the line. Please stay on the line. Please stay on the line. See this here. Okay. Okay. Now, this is the concept of, from the definition of linear space or vector space. Here, V under addition is an abelian group. Here, addition represented as the vector addition. Under vector addition is one of the binary operation throughout the vectors. And second condition is scalar multiplication holds good. And third condition is the distributivity. Here, scalar distributes under vector addition, or at the same time, here V under addition is an abelian group, means here the V1 to V5 conditions: closure, associativity, identity, existence of inverse, and commutativity. When these five laws or properties or conditions or axioms or laws is there, okay, postulates. Now, when these five laws are satisfied, that is called an abelian group is there. Okay. Second condition is, already we have what is the abelian group is there. Okay. Already we have learned in under modern algebra is there, and throughout the algebraic paper. So that is the paper 1 in the previous MSc previous year. Okay. Second one, scalar multiplication holds good. What is the scalar multiplication? First of all, so you are taking the one of the field of the element is there. So suppose A be any one of the field element. Here A belongs to capital F and belongs to represented as either, we must read as either belongs to or is in. Okay, A belongs to F or A is in. So that is the representation. And second one is the one of the vector is there. Here alpha being any one of the vector. Alpha being any one of the vector is there. So here A alpha is also belongs to V. So that is called scalar multiplication holds good is there. Okay. Next, third one, the scalar distribution is there. What is the scalar distribution? Okay. What is the scalar distribution? Scalar distribution, now here the distributive holds good is there. Suppose 1 into alpha equal to alpha, here alpha being any one of the vector, so that is alpha belongs to V. And at the same time, A of alpha scalar distributes under vector addition, that is A of alpha plus beta. So here alpha and beta be any two vectors. So A be any one of the field element is there. That is A of alpha plus beta equal to A alpha plus A beta is there. And the second one is A of alpha plus beta and A of alpha beta, that is A alpha of beta is there. And at the same time, A plus B of alpha. Here the A and B are any two field elements, alpha be any one of the vector. Here vector distributes under scalar addition, under addition. Okay, A plus B of alpha is A alpha plus B of alpha. Now, when these four distributivity conditions, they must satisfy, it must satisfy any two is there. Okay, that is A of alpha plus beta equal to A alpha plus A beta, and A plus B of alpha equal to A alpha plus B alpha, and at the same time AB of alpha equal to A of B alpha, and A of alpha beta equal to A alpha of beta. Finally, 1 into alpha equal to alpha. Here for all alpha and beta be the vectors, and A and B are any two field elements is there. So when these conditions are satisfied, that is called a real linear space, linear space is there. So at the same time, that is also called vector space. Okay. Students, listen carefully. And according to that vector space definition, already we have learned in the vector analyzation of the concept under UG level, and then the continuation part of in the first year, MSc first year, that is the previous paper. Paper 2 is the real analysis. We have learned the vector space or linear space, and so many examples under vector space definition. Okay. Suppose when the field of the elements are called. Now this is the introduction of the functional analysis. Once I have to repeat here, that is your understanding purpose. Okay, that is the recall of the entire part. Okay, throughout the analyzation. Okay. Next one, when the field of the elements are called, that is the structure of vector space is V of F under addition under multiplication, and at the same time, those here the field of the elements, when the field of the elements are called real numbers, that is represented as V of R under addition under multiplication, that is called real linear space or Euclidean space. So that is also R power n of R. So n tuples of the real numbers through under vector addition under scalar multiplication must be a vector space or linear space. And here this is the contents of functional analysis. Now enter the paper is totally 18 units here. One is the unit 1 normal linear space. And first of all, so we must introduce the definition is real, that is the linear space. And here the field of the elements are complex numbers. So that is also represented as V of C under addition under multiplication or C power n under vector addition under scalar multiplication. That is called complex inner product space or a unitary space. That is the definition of real linear space or complex linear space. So those definitions, according to that definitions and some other examples may be referred in now enter the part of real analysis, throughout the part of real analysis, or in sometimes complex analysis is also sometimes also referred. And at the same time, so according to that the inner product space definition, now we have to introduce the norm. What is the norm? So here the basically now the basic definition from the definition of basic concept, some other basic concepts. Unit 1 is a normal linear space. Now, what is the norm? Norm is also introduced in the part of two. Just we are taking any one of the vector is there. Here x being any vector, alpha being any vector. Here any vector is there. So here x and y be, there are two vectors here. Inner product of x and y. What is the inner product condition? IP1, IP2, IP3. When these three conditions are satisfied, that is called inner product space. Already we have learned in under UG level, and also at the same time real analysis paper is there. And according to that, what is the norm? We are taking any one of the vector is there, x being any one of the vector, then their norm represented as double mod of x. Norm means from the definition of inner product of x and y means, so you are taking the y, put y equal to x, inner product of x and x. So that is called a double mod of x. Double mod of x means square root of inner product of x and x. So that is the definition of norm is there. So according to the linear space, what is the normal linear space? That is the first unit, okay. And definition of normal linear space and examples, it is on briefly, okay. Now, unit 2 is Banach space. Now, that is the enter the first of all, we must introducing what are the units and what is the basic concepts, enter all the units. Okay, and without the normal linear space, we can't imagine the Banach space is there. When a normal linear space is called, that is called a Banach space. A normal linear space is called, that is called a Banach space is there. And third unit is bounded linear transformation. What is the boundedness? Already we have introduced the vector space from the under the vector analyzation under the UG level. What is the linear transformation? What is the bounded? Okay, so that is the unit 3. Linear transformation means T maps U to V or T maps V to W. Here U and V be any two vector space or V and W or V and W be any two vector spaces is there. Already here V represented as the vector space or linear space and W be the subspace of a vector space. So transformation is defined from domain to codomain, or here T maps V to W or T maps U to V be a mapping is said to be a linear mapping. Linear mapping means throughout the conditions under the vector addition, under the scalar multiplication, or directly a necessary and sufficient condition of A alpha plus B beta. So that is one of the subspace condition, or alpha plus beta and here A alpha. There are two conditions from those from their conditions, a necessary and sufficient condition to be a subspace. So according to that conditions, we must we must applying those conditions in the linear mapping. So that is called linear transformation or homomorphism on vector space. So that is transformation of alpha plus beta equal to T of alpha plus T of beta for all alpha comma beta belongs to V, and transformation of A alpha equal to A into transformation of alpha. So that is the two, there are two conditions you have applied on the linear map part. So that is called a linear transformation. And the direct condition is transformation of alpha plus b beta equal to A into T of alpha plus B into T of beta. So those conditions, according to that linear transformation, we have learned the zero transformation and identity transformation is there. Okay. T of 0 equal to 0 cap, 0 crown is there, 0 cap or 0 crown. So that is one of the representation. Okay. So that is called zero transformation. Okay. When the I of alpha equal to alpha, that is called identity transformation. So according to those definitions represented in unit 3, that is the linear transformation. So when it is bounded, so bounded concept is already we have learned in the real real number system. Okay. So fourth one, finite dimensional. What is the finite dimensional? Okay, there exists a number of bases is called the dimensional. The number of bases of a vector space, that is called the dimensional. So when the dimension is finite, that is called finite dimensional throughout the normal linear space. That is the fourth unit, finite dimensional normal linear space. And the fifth unit is, what is the dual of Banach space? So already just you have to explain the concept of Banach space. Okay. Now, according to this explanation, just we have to understand understanding purpose. Okay. Now that is the entire the concept. First of all, we must learn the all the units thoroughly. Just you have to see and refer the and all the units. So dual of Banach space. What is the dual of the part? So image of the Banach space is called a dual. So that is also represented as n dash or n star, whatever it is. Banach space means a normal linear space which is complete. That is called a complete normal linear space is called Banach space. So without the normal linear space definition, we can't imagine the definition of Banach space. Okay. Now, what is the dual of Banach space? Dual means that is the n star and n double star. So that is the dual nature. Okay. Now, this is also referred in the operation research paper. What is the duality? Okay. So, enter the each and every content must be connecting each and every paper is there. Okay. Dual of Banach space. Next one of the important theorem in the functional analysis, Hahn-Banach theorem. Okay. Hahn is one of the mathematician and Banach is also one of the mathematician. Now, both concepts are same. Now, that Hahn-Banach theorem, okay, this is also one of the important theorem in the final examination. Okay, so don't forget. Now this is the one of the must and should given this theorem in the final examination. Okay, next one, open mapping theorem. Banach is one of the mathematician. Don't forget this one. Okay, open mapping theorem. This is also one of the important theorem, and that is the unit 8 closed graph theorem is there. What is the closed graph theorem is? Okay. So that is the deduction of the open theorem is closed graph theorem, and the ninth one is principle of uniform boundedness. So at the same time, this theorem is also called bounded Steinhaus theorem. Unit 9 is principle of uniform boundedness or bounded Steinhaus theorem. Okay. Next one, what is the inner product space? That is the 10th unit. So in short form as IPS. So that is called inner product space. So some other examples are also there. And what is the real inner product space? What is the real inner product space is called Euclidean space, and complex inner product space is called unitary space. So those definitions also depends upon the normal linear space part. Okay. Now, what is the Hilbert? Hilbert is also one of the mathematician. Now, that mathematician, he is one of the great mathematician is here. Now, Hilbert is also explained throughout the space nature. So, what is the Hilbert space? Definition and some other theorems. Okay, those theorems are very important in the final examination. Okay, Rice-Fisher theorem and Rice representation theorem. Enter all the theorems involved in Hilbert space. That is the unit 11. What is the orthogonality in Hilbert space? We are taking any two vectors. Here the orthogonality means orthogonal. Means that is the orthogonal condition is the perpendicular of this part. Here we are taking in any two vectors. So those vectors represented as mod inner product of x and y equal to 0. So inner product of x and y equal to 0. That is called orthogonal. In sometimes that is also representation x is perpendicular to y. So x is perpendicular to y means so see this one. Okay. See this one. So that is unit 12, orthogonality and orthonormal. So at the same time, one of the important theorems here, the one of the important theorems here. So what is that? Cauchy's quasi inequality in an inner product space, unit 10, and parallelogram law, triangle inequality, Parseval identity, Bessel inequality, all the theorems involved in entire these units. Suppose we have to practice 10th, 11th, 12th, 13th units. Now easy to get and get good marks. The first 3 units and at the same time, first 13 units there, that's enough. Now from the 13 units, we have to refer without a duality, without a dual of Banach space of that unit, just easily to get out of 70 theory, they will be, now enter the students, please, you get out of 70 to 70 marks easy to get and easy to achieve here. Okay. Now, just you have to refer in the previous papers. Okay. Now I will give in the final session, final session of online part, I will give some other model papers are also here. And here, just you have to see, and according to the orthogonality and orthonormal, Gram-Schmidt orthogonalization, not here, Gram-Schmidt orthonormalization process. This is GSOP theorem. Gram-Schmidt orthogonalization or orthonormalization process. Okay. Now some other inequalities in Hilbert space. What is the Rice-Fisher theorem and Rice representation theorem? Okay. Now that is the 13th and 14th units. And at the same time, 15th unit is orthogonal complements and 16th unit is what is the bounded linear functionals on a Hilbert space. Now this is also one of the simple concept from the third unit, according to the third unit referred in, and that is also one of the implication of unit 16th, bounded linear functional on a Hilbert space. Now there are projection theorem. Now one of the important theorem is the projection theorem in this unit, and according to that, orthogonal complement 15th unit. Okay, 16th unit some other properties, and 17th unit is linear operators, bounded linear operators on a Hilbert space. Okay, now that is unit 17th is very simplest concept and easy to understand. And according to this 17th unit, easy to get and easy to achieve in the final examination from this unit. One essay question is given and some other, in sometimes 2 short answers is given from unit 17th is there. Okay. Now unit 18th, finite dimensional spectral theory. Now this is one of the direct theorem in the now in the final examination, that is the question number 8, spectral theory. State and prove finite dimensional spectral theorem. Okay. Now, sometimes short answer is given, simple short answer is given in this unit. Okay. Now, that's enough. These are all 18 units. Just you have to see the first one. What is the normal linear space? Almost all. Okay. Please stay on the line. Please stay on the line. Please stay on the line. Okay. See here, students, this is the normal linear space definition. See, and first of all, so you must observe each and every definition is here. What is the normal linear space? Already we have introduced the linear space definition. So here, already that is the a linear space. Means here the linear space represented from the starting letter is capital L. So that's why represented as the linear space is capital L. In sometimes this is also called a that is the original origin of the from the part of throughout the vectors. So that's why that is also it is also called vector space. A linear space means that is the L. So that is the from the beginning of the letter easy to understand here. Here L be any one of the linear space. Here the set of objects is called vectors. Already explained here. Here the binary mapping is here any one of the binary operation L cross L to L. Here L be any non-empty set of a mapping. So that non-empty set of a mapping in the field of the elements, in the domain of the elements are called field of the elements. So that's why here the represented as F cross L to L. Here F is the field of the scalars. Is either those field of the scalars represented as throughout the real numbers or complex numbers. So either real numbers means you are taking the real numbers, that is the real number field, or suppose you are taking the complex numbers, that is called complex number field is there. Okay. Now these operations under the vector addition and scalar multiplication throughout the vectors and scalars. Now it is said to be a linear space. Here, what is the L1? L1 means that is the here first of all L1 is the actually throughout the systematical order closure law, associative law. Already we have know that the some other the concept closure, associative, existence of identity, and existence of inverse. When these four are satisfied, that is called a group. And in addition that, when the fifth law is also satisfied, that is called abelian group under the vector addition. Now, here the represented as here under vector addition means already you are taking any two vectors x plus y is also belongs to L. That is the when the x and y be any two vectors under vector addition. So here x plus y, that is the represented as addition is closed in between the two vectors. So that's why that is the closure condition. So there is no problem. At the same time, x plus of y plus z. See this one, that is the L3. Now that is the representation here. L3 is here. Now in the systematical order, L2 is associative law. L3 is existence of identity. L4 is what is the L4? Existence of inverse under the vector addition. L5 is the commutative property. Okay, but here already through without the concept of closure condition, now we are given that here L1 is suppose we are taking any zero vector is there. So that zero vector is also belongs to L. For all x belongs to L is there. Here x being any one of the vector. Now this is the existence of identity. So x plus 0 bar equal to x or 0 bar plus x. Here 0 bar, that is the represented as a vector is there. Without bar notation, here 0 bar or 0 cap, whatever it is, x plus 0 bar equal to x. That is the existence of identity. So here 0 bar, we are taking the right side, right identity is there. So that's why this is the right identity, and 0 bar plus x equal to left identity. We are given the same vector, that is x. Okay. So non-empty set of element is here. Okay. Now under the vector addition, how to arrange the using vector addition identity of the vector, how to get the same vector is there. Given the set of the element. Element means here one of the vector is there. So x plus 0 bar equal to x. Here 0 bar represented at right side. So this is the right identity, and the left identity is 0 bar plus x equal to x. Okay, here 0 bar be the additive identity. And L2 is already these definitions are all well known. Here x being any non-zero vector is there. Non-zero means inverse exists. You must understand here. According to this concept, then easily to understand enter the algebraic concept or either algebra, enter each and every paper is there in post-graduation level. Okay. Here, x being any one of the non-zero vector, that non-zero vector means inverse exists. So minus x is also belongs to L is there. So how to get the additive identity by using by using the non-empty set of vector, non-empty set of element. So x being the non-zero means inverse exists. So x plus of minus x or minus of x plus x equal to 0 bar. And what is the L3 is there? This is the associative under the vector addition. X plus of y plus z equal to x plus y of plus z. And this is the associative under vector addition. L4 is, that is the commutative under vector addition, x plus y equal to y plus x. Now, these are all conditions already. Now, this is also already we have learned in UG level in this paper of algebra. Okay. And also, one of the connectivity paper is first year algebra paper is there. Okay. This is the commutative property. And L5 is here alpha being any one of the scalar distributes under vector addition or linear space, linear elements. Here x and y linear elements means those elements are objects. We are treated as under vectors. Here x and y being any two vectors, alpha being the field element, alpha of x plus y. So scalar distributes under vector addition, alpha x plus alpha y. Already we know that one of the scalar multiplication. Here alpha x be the scalar multiplication. That is one of the closure condition under scalar multiplication. So throughout the closure conditions under vector addition under scalar multiplication, now according to the L1 to L8 properties, these properties are satisfied. That is called linear space. Here alpha, these are all L5 to L8. These are all called distributivity conditions. Now the entire any two distributivities are satisfied. That's enough. Enough to any two distributive properties are satisfied. Okay, alpha of x plus y equal to alpha x plus alpha y. Here alpha being the field element. And at the same time, alpha and beta be any two scalars or field elements. Alpha plus beta of x equal to alpha x plus beta x. And L7 is there. Alpha beta of x. Alpha beta of x means alpha of beta x is there. And L8 is 1 into x equal to x. Okay, now this is the multiplicative identity is here. Here the multiplicative identity is 1. So that's why we can write as that is 1 into x equal to x. So here alpha beta of x means alpha beta be any two scalars. By using scalar, alpha beta of x equal to alpha of beta x, and L8 is 1 into x equal to x. So here enter all the concepts. Okay. Enter all the concepts satisfied. Now L1 to L8 properties. Okay. L1 now from the conditions of closure condition, L1, L2, L3, L4. And then after that, in between L5 to L8, any two are satisfied. Now that is called a vector space or linear space. Now these basic properties are all well known. Now 0 into x, because 0 means that is the additive identity is there. 0 vector means that is the group identity in L7. What is the L7 property? 1 into x equal to x. And according to that, under vector addition, 0 can also be written as 0 plus 0 of x equal to 0 into x from the distributive condition. So 0 into x plus 0 into x by L6 property. Now 0 into x equal to 0 bar. That is the simple elementary property. Okay, minus 1 of x equal to minus x, because 1 be the multiplicative identity. Now that multiplicative identity, from the multiplicative inverse, how to get the multiplicative inverse? Because here x being the non-zero element is there. So every non-zero element must possess with multiplicative inverse is there. So that's why here x being any one of the vector, that non-empty, that vector is non-empty means non-zero vector. So we are getting, what is the meaning of non-zero vector? So inverse exists. So how to get the minus x? Minus x can also be written as minus 1 of x. So that's why, so that is 0 into x. 0 can also be written as by using 1. Okay. Now that is 1 is the multiplicative identity. According to that, 1 can also be 1 plus minus 1. 1 plus of minus 1 of x. So minus 1, 0 into x can also, by using this one, 0 into x equal to 0 bar. And how to erase the, how to write the 0? by using a multiplicative identity. So that is 1 plus minus 1 of x equal to, that is 0 into x equal to 0 bar. So again 1 into x from the distributive condition, 1 into x plus minus 1 into x equal to 0 bar. So again 1 into x means x is there, x plus of minus 1 of x equal to 0 bar. And again minus 1 of x equal to, so that is again this x converting into this side at left side, no, that is minus x is there. Okay, now here the field of the elements are real numbers, that is called a real linear space. Okay, now that the definition here mentioned here. So here end of the 1.3.2, this is when the field of the elements are real numbers. Okay, so those real numbers of the real linear space is called a real linear space or Euclidean space. Okay, so that is 1.3.2. This is one of the example of linear space, and at the same time 1.3.3. Now this is one of the example of n tuples of the field elements can also be written as, we are taking x being any one of the vector. That vector can also be written as, we are taking n tuples of the elements x1, x2, so on, xn. So these elements represented as xi elements. Those xi elements are that is the from the linear part, given the non-empty set part. So n tuples of the n tuples of the f can also be written as, here x being any one of the vector, that vector can also be written as, we are taking the n type of elements x1, x2, so on, xn. So enter that n type of elements can also be simply represented as xi. Here I varies from, so in between 1 to n is there. Okay, so that's enough. Now linear space conditions, all the L1 to L8 conditions are satisfied, that is called linear space. So that's enough. That now these examples are maybe now already previously referred in the vector spaces concept or linear algebra paper under UG level or and also in the first year real analysis paper. So n tuples of the field elements, n tuples of the arbitrary, that is also a linear space. Okay, so that is represented as f power n under addition under multiplication is a linear space. All the axioms are satisfied. So all the axioms means, this is again for your understanding purpose, once I have to repeat here from the beginning of this part, linear space. L1 to L8 axioms are satisfied. So that is called linear space by using the n tuples of the elements. Okay. Now, this is also at the same time when the field of the elements, here the field of the elements are complex numbers, that is called complex linear space, that is denoted by C power n. Field of the elements are real numbers, so that is f power n. It referred as n tuples of the field, n tuples of the linear space, f power n. So that linear of the elements are called real numbers, that is represented as r power n. So here n be the arbitrary of real numbers. So a system of double script r, it read as script r or n tuples of the real numbers is also a real linear space, and complex n tuples of the complex linear space is called a unitary space. Okay, this is Euclidean space or real linear space. This is complex linear space or unitary space. Okay. Now, at the same time, see this example 1.3.4. Now, it read as, what is the script C of AB? Script C of AB means with the set of all continuous real valued functions. Now, it read as the set of all continuous real valued functions on closed interval AB. What is the closed interval? So, interval can be divided into, here any non-empty set of a mapping is said to be an interval. It is consisting at least two elements. Each element lies between any two members. That is the definition of an interval. Okay. Now, intervals are four types. Closed interval, that is the square bracket of AB. Now, each and every notion you must be known is here. Okay. Now, it read as closed interval AB. So, some students are also directly, direct questions is also practiced here. And that practice of the, according to that practice, we are representing in the examination. But by using of the subject, enter the concept, when you must know the concept, then automatically easily to achieve each and every paper as well as well known. Okay. Now, here the C of AB means be the set of all continuous real valued functions defined on the closed interval. Now, closed interval means here x being any one of the element. That element lies between A and B is there. So, x from x being closed interval AB means A less than or equal to x less than or equal to B. Now, here the less than or equal to represented as the closed interval of this part, and open interval particularly it is represented as in the less than of this part. So, closed interval means A less than or equal to x less than or equal to B. So, those closed intervals be the set of all continuous. This is the representation of C of closed interval AB means the set of all continuous closed real valued functions defined on a closed interval AB under the vector addition and scalar multiplication over the real numbers. So, we are taking any two set of all real valued continuous functions, that is FG, or at the same time H is also there, F, G, H, whatever it is. Now, these are all real valued continuous functions, alpha being the real number and x being the element. So, because why do you taking the that element? F represented as f of x, g represented as g of x. So, set of all continuous function means with respect to the element is g of x or f of x and h of x. Be the set of all continuous real valued functions. Here alpha being the constant. So, that is the field of the element is called a real number. So, what is the closure condition? The set of all real valued functions. We are taking any two functions f plus g with respect to x equal to f of x plus g of x. This is the vector addition is closed under the set of all continuous functions. Scalar multiplication. We are taking any one of the real number, set of all continued function, alpha f of x equal to alpha of alpha into f of x. So, we are taking f plus g, that is also simply simple that f plus g is also belongs to C of AB, because sum of any two continuous functions. So, sum of SUM sum or addition of any two continuous functions is f plus g is also belongs to C of AB. At the same time, alpha f is also continuous function, because alpha being any one of the real number. F means f of x. Alpha f equal to f or alpha into f of x equal to f of x, whatever it is. Okay. What is the zero function? This is the under the linear property L1 to L8. When the L1 to L8, when these conditions are satisfied, that is called a linear space. 0 with respect to the function is 0 bar of x equal to 0. So, 0 bar means that is the real continuous function with 0 identity is there. 0 identity of the continuous function represented as 0 bar of x equal to 0. That is the L1. Okay. So, f plus 0 bar of x equal to f of x plus 0 bar of x, and again we are getting the f of x is there. Simply notated as f plus 0 bar equal to f. Okay. Next, here the 0 function means a 0 vector in C of AB is there. Okay. C of AB is there. So, L1 is verified and L2 is, please stand the line. Okay. L2 is there. F plus minus f of f plus minus f equal to 0 bar by the equality of two functions. So, L2 is also verified, and L3 is, we are taking any three functions f plus of g plus h or f plus g of plus h of x equal to f of x plus g plus h of x. So, this is the associativity with respect to the set of all continuous function L3. L4 is commutative under vector addition f plus g equal to g plus f. With respect to x is f plus g of x equal to g plus f of x. Simply f plus g equal to g plus f is there. L5. What is the L5? Scalar distributes under continuous real valued functions. Alpha of f plus g of x equal to alpha f plus alpha g with respect to x. Okay. Now, in every time represented as for all here x being the element in between a and b, that is the closed interval of the part. So, that's why that is the meaning of a less than or equal to x less than or equal to b. So, that's why f comma g is also belongs to C of AB. Now the script C of AB means a set of all continuous real valued functions. So L5 is verified and the distributivity condition L6, L7, L8. Okay, well, now here L6 is simply with respect to the identity 1 into f of x equal to f of x, or simply 1 into f equal to f is there. And at the same time, alpha plus beta of f, that is means alpha plus of beta f, that is alpha plus beta of f equal to, that is alpha f of x plus beta f of x. Okay. So that is simple representation. And L7, that is alpha beta of f, can also be written as alpha of beta f. Okay, L8 is 1 into f equal to f, L6, L7, L8, and now With respect L5 is also there. When these four properties, any two are satisfied, that is called a by the L from L1 to L4 is common part. And in addition that from the beginning of closure condition and L6 to L5 to L8, any two are satisfied, that is called a linear space. So one of the example of the set of all real valued continuous functions is also a linear space. Okay, there are so many examples. It depends upon the linear space part. So 1.3.5, this is also one of the well-established example from the derivations of the derivable functions. Here capital X be the, now this is one of the practice, for your practice purpose, 1.3.5. Capital X be any one of the non-empty set. That non-empty set is a real linear space with the real addition and real scalar multiplication. Here real scalar multiplication means those functions are real functions. Here capital X equal to f, g, h, whatever it is, such that f maps R to R. So here, what is the f? It has the derivatives of all orders. Okay. Now these inequalities are very important from the beginning of a linear space definition. Now those inequalities are also referred in under UG level and also real analysis paper in the PG first year. Okay. The first one is well known. Some other inequalities are there. What are that inequalities? Cauchy-Squarge inequality, from the Cauchy-Squarge inequality is also referred in the Holder-Minkowski inequality. Now, first of all, Holder inequality. Now, these inequalities, okay, these inequalities, so this is P is greater than 1. This is the first inequality is Holder inequality on the sets, and second one on the sequences, on functions. There are three types of inequalities mentioned here. Now this is on the sets part is there. Okay. On the sets part, here P is greater than 1. So this is the first inequality, Holder inequality on linear space part, when P is greater than 1 and Q is also defined. So 1 by P plus 1 by Q equal to 1. That is the condition of part here. Then we have summation modulus xi and yi. So mod representation. So summation means overall the part. It varies from 1 to n. Mod xi yi is less than or equal to summation of mod xi whole power p and whole power 1 by p into summation mod yi whole power q and whole power 1 by q. This is the inequality of Holder inequality. So mod xi yi norm xi, okay, this is one of the representation of Cauchy-Squarge inequality. So according to that, first of all, we must here the mentioned inequality is Holder inequality when P is greater than 1. Suppose P and Q, any two real numbers are there. Okay, so here the complex numbers. So elements are x elements and y elements are complex numbers, and according to that, P and Q be any two elements. So here P, when the P is greater than 1, because in the denominator of the given the condition P and Q, if it is greater than 1, then it must be satisfied here. Okay. Now suppose P equal to 1, we are getting 1, Q equal to 1. Okay. So 1 plus 1 is 2 is there. So that is not satisfied here, the condition. So P is greater than 1 means suppose P equal to 2. So because greater than 1 value is 2 is there. So 1 by 2 plus 1 by 2. So 0.5 plus 0.5 we are getting the 1 is there. So hence the condition of P is greater than 1, q is defined by 1 by p plus 1 by q equal to 1. Then we have summation mod xi yi is less than or equal to summation mod xi whole power p and whole power 1 by p into summation mod yi whole power q and whole power 1 by q. So I varies from 1 to n. So I varies from 1 to n here. So here the xi values, yi values are represented as the complex numbers. What is that? Complex numbers. See this proof. Say given the condition, say this is the first equation. This is the first equation. So now not mentioned here, and from the beginning of this proof, given condition is we are taking this is the first equation. First, we shall prove that a is greater than or equal to 0. Some corrections are here. Please note down. And each and every step must observed here, because without observation you can't we can't some other, okay, you have to gun the some other doubts are also repeated here. Here a and b, any two numbers, so those elements are greater than 0. So we are getting that a power 1 by p plus b power 1 by p is less than or equal to, so this the condition is okay, a by p plus b by p. So this is the second equation. Suppose any two numbers are here. So first of all, we shall prove the condition, that is a power 1 by p plus b power 1 by p is less than or equal to a by p plus b by p, b by q. Okay. Now from the second equation, it is obvious. Suppose you are taking the a0 over b0. So we assume that a is greater than 0, b is greater than 0. Now the condition is, our assumption is t being any one of the real number. So x of t equal to, this is our assumption, 1 by q plus, because a is greater than 0 means, suppose that value is 1. Okay. 1 by q plus t by p minus t power 1 by p. That is our assumption. Okay. So our assumption is, that is according to our assumption, x of t equal to 1 by q plus t by p minus t power 1 by p is there. Now, according to our assumption here, x after the derivation of this part, x dash of t equal to, so this is without t is there, so this element is 0. T derivative is, because this with respect to the t, so we are getting the value is 1. So 1 by p of 1 minus t power 1 by p derivative is 1 by p into t power 1 by p minus 1. Okay. T power 1 by p into, so 1 by p is common here. So in this term, 1 by p minus 1 by p into t power 1 by p minus 1. So that is the derivative of t power 1 by p. So t by p derivative is, t derivative is 1, 1 by p is here. And here the coefficient is 1 by p, because derivative of x power n is n into x power n minus 1. We are applying here t power 1 by p is 1 by p into t power 1 by p minus 1. 1 by p is common. So we are getting 1 minus t power 1 by p minus 1 from the condition is, what is that? 1 by q. So because 1 by, already we know that, given the condition is 1 by p plus 1 by q equal to 1. So 1 by q equal to 1 minus 1 by p. So that's why after the substitution, 1 by p means minus 1 by q is there. Okay. Suppose t is less than 1. Here the derivable of x of t is less than 0. When the t is greater than 1 and the derivable of x of t is greater than 0. So that is the ultimate of the conditions, t less than 1. So derivable of x of t less than 0, t greater than 1, derivable of x of t is greater than 0. Okay. Consequently, here x of t is an increasing function. This is when given the increasing function, given the derivable of the part is the increasing function, for t is greater than or equal to 1. Okay. For all t being the real number, x of t is less than or equal to x of 1. So that value is 0. Okay. So t power 1 by p from the above condition can also be written as enter that value is greater than or equal to 0. So this value is t power 1 by p is less than or equal to t power 1 by p is less than or equal to 1 by q plus t by p. So this is t power 1 by p. This value is converting because enter this value is 0 is there. This value is 0 is there. So t power 1 by p is less than x of 1 equal to 0 because replacing t equal to 0 here. So t equal to 1 is there. So x of 1 equal to 0. So we are getting the value is t power 1 by p equal to 1 by q plus t by p is there. Okay. From the now here by using what is the x in x of t value? X of t value is our assumption is, so say this is the third equation, or already the second equation here, say we are using in the put t equal to 1 in x of t value, we are getting this condition. T power 1 by p is less than or equal to 1 by q plus t by p. So suppose t equal to a by p, a by b is there in second equation. Okay, inequality in the first condition, given the inequality is first condition, it is obvious. Okay, now here the left or right hand side of this part is 0. So we are getting the terms summation mod xi whole power p and summation mod yi whole power q, both are different from 0. So we are applying the inequality second condition to the numbers. So this value is ai and aj and bj. So ai equal to, this is I, not aj and bj. Okay. So aj value is mod xi whole power p by mod summation mod xi whole power p. bj value is summation mod yi whole power q by summation mod yi whole power q. Here I varies from 1 to n. Already j is also varies from 1 to n is there. Okay. Now each and every term a1, a2, so on an, and b1, b2, so on bn. Now enter all the values substituting here. But in the different genre here, it is different from 0. That's we are taking in terms of j values aj and bj. That is our assumption in the second equation. aj equal to mod xi whole power p by mod xi whole power p. bj equal to summation mod yi whole power q by summation mod yi whole power q. That is our assumption. So mod, now after the production of this one, producting of these values, summation mod xi into yi by summation mod xi whole power p into summation mod yi whole power q equal to, so p converting into this side 1 by p, so q converting into this side 1 by q is there. So aj whole power 1 by p and bj whole power 1 by q. So that value is less than or equal to, already we know that our assumption of the above this concept. So say this is the second equation. That value can also be written as a by p plus b by q. Okay. After the substitution a by p plus b by q here. Okay. A means aj, b means bj. Okay. Adding all the inequalities, summation, applying on both sides summation mod xi yi by summation mod xi whole power p and whole power 1 by p, summation mod yi whole power q and whole power 1 by q. Okay. Now, 1 by p, okay, summation mod aj. Now, this value can summation mod aj by p. Summation is also applying here. Summation mod aj, summation mod bj. So, j varies from 1 to n. That value is an equivalent to 1 by p plus 1 by q equal to 1 is there. So, summation mod aj equal to summation mod xi whole power p by summation mod xi whole power p equal to 1. Summation mod bj equal to summation mod yj whole power q by summation mod yi whole power q. Okay. This value is I, not j. This is I. Please rectify this one. This is I. So, summation mod yi whole power q equal to 1. Finally, we are getting summation mod xi yi is less than or equal to summation mod xi whole power p and whole power 1 by p. Summation mod yi whole power q and whole power 1 by q is there. So, that is the simplest application. Okay. Suppose p equal to q equal to 2 in a Hölder inequality. This is the end of this proof. So, one of the application is, so what is the Hölder inequality? Summation mod xi yi is less than or equal to summation mod xi whole power p and whole power 1 by p, summation mod yi whole power q and whole power 1 by q. Suppose one of the result is, just you have to see and refer this one of the result. Substitute, after the substitution, p and q both values are, we are taking that is the two value in Hölder inequality. So we are getting the Cauchy's quasi inequality. So already we have proved Holder inequality. In that inequality, you are substituting 2 is there, P and Q, in the replacing of P and Q by 2. So summation, now we are getting the Cauchy-Squarge inequality is there. Summation mod xi yi is less than or equal to summation mod xi whole square and whole power 1 by 2. So this is norm x. What is the norm x? Norm x means square root of xi square. Whole power 1 by 2 means square root of summation mod yi whole square whole power 1 by 2. That is square root of. So this is this value norm x. This value is norm y. So summation mod xi yi is less than or equal to that is norm x into norm y. So that is called from the state and prove Cauchy-Squarge inequality from Holder inequality. Means we are just we have mentioned from the Holder inequality 1.4.1 and we are taking in the replacing the P and Q by 2, we are getting the Cauchy-Squarge inequality. Okay, students, this is 1.4.2 for sequences purpose. Now the above inequality is from the sets. Okay. Now here, especially for sequential purpose, what is the sequence? Now already we have learned in the established theory for the real sequences, and according to that, here xn, yn be any two sequences. Now particularly in examination is given state and prove Holder inequality for sequences. You must present and replacing of this theorem. Okay, and the above theorem is also just you have to for your purpose just little bit considered here. Okay, now here the Holder inequality for sequences is there. Xn, Yn be any two sequences of scalars with respect to the real numbers and complex numbers such that summation mod xi whole power p less than infinite, summation mod yn whole power p less than infinite. Because here xn, yn be any two sequences under their summation of the values less than infinite on the p spaces nature. Okay, here p is greater than or equal to 1. So finally summation mod xn yn is less than or equal to summation mod xi whole power p and whole power 1 by p and summation mod yi whole power q and whole power 1 by q. Now here the condition is 1 by p plus 1 by q equal to 1. Here p is greater than 1 is there. Okay. Now see here. Now particularly please practice these theorems, very important in the further session. Okay. For any positive integer, m be any one of the positive integer is here. Okay. Please stay on the line. Please stay on the line. Okay. Now, for any positive integer, m being any one of the positive integer, by Holder inequality, already from the Holder inequality assumption is given the statement, given the statement in the above part, summation mod xi yi is less than or equal to summation mod xi whole power p and whole power 1 by p, summation mod yi whole power q and whole power 1 by q is there. So enter this value less than or equal to from the above theorem in the first equation, given the statement summation mod xi whole power p and whole power 1 by p into summation mod yn whole power q and whole power 1 by q. Okay. Now, from the partial sum of the series, summation mod xn yn are bounded. On the left hand side of this part, when the left hand side LHS is bounded, then automatically summation mod xn yn is finite. Okay, summation mod xn yn is an equivalent to that value can also be written as throughout the limit and m tends to infinity to summation mod xn yn. So limit is also applying given this partial sum. So that is less than or equal to summation mod xn whole power p and whole power 1 by p, summation mod yn whole power q and whole power 1 by q. Because given the summation is partial sum is bounded. So bounded means we are applying we are taking the nature is limit nature is there. So here the limit m tends to infinity because it varies from 1 to m values. Okay, m varies from 1 to so that is the 1 to m values. So here the m represented as the infinite. So directly we are getting the summation 1 to infinity because when the limit is also bounded here. So bounded means it is finite. Finite means in a particular value is 1 to m is there. So just we are taking it, just you have to imagine the limit m tends to infinity is there. Okay. So P be the positive real numbers and X be an arbitrary measure space. Arbitrary measure space with measure is mu. Mu be the measure. So LP spaces be the set of all. What is the LP? LP, the set of all measurable functions f defined on X. Students, listen carefully. Now, without the concept, you can't mention the, please, either internal assignment or external in the final examination theory paper. Okay. So question is, one question is given, but answer is entirely different from the given the question. Okay. Don't deviate here. Okay. Please understood here. Okay. Now enter so all the students. So yes, all the assignments is entirely different from the given the question paper. Okay. Please understand here. So that is not correct. Okay. So given the question, when the given the question, then automatically you must present the concerned question of the answer. Okay. Without that, you can't do it here. Okay. LPB, what is the LP? LP be the set of all. Measure means that is the length. What is the measure? Measure space means measure means that is the length. Okay, here length means mu be the measure. So LP be the set of all measurable functions f defined on capital X. But is here particularly here mod fx. Linear space of the element is f of x. Linear space of the element is f of x. So that's why mod f of x whole power p is integrable. Suppose in examination is given, that question is state and prove Holder inequality for sequences. Okay. ORR, prove that LP equal to, here LP is the, we are taking the one of the measurable function is there, measure function is there, F, G, H, whatever it is. So here that function is measurable, means integral X mod F P mod F whole power P d mu is less than infinite, is also. So mod f of x whole power p is integrable means you must mention the Holder inequality for integrals. Okay. Please understood here. Okay. 1.4.3. This is for integrals on Holder inequality. So f and g be any two measurable set of all measurable functions. P is greater than 1 and 1 by p plus 1 by q equal to 1. That is the condition. So the product of any two functions given the measure is 1. Fg, yeah, f into g is also belongs to L1 is there. Okay. See this statement. Okay. Now here integral x, here x be the set of all. What is the capital X? Arbitrary measure space. On arbitrary measure space throughout the integration mod fg of d mu. So d mu means that is the measure space, measurable part. So mod fg of d mu is less than or equal to integral x mod f whole power p d mu and whole power 1 by p. So we are applying the integral throughout the integration. Now this is the for integrals purpose on Holder inequality. So integral mod g whole power q d mu and whole power 1 by q is there. So this is one of the finest theorem throughout the integration. So say, similarly, we are using the proof is we shall make use the following inequality. Established the Holder inequality is all the first condition is there. The product of AB is less than or equal to A power P by P plus B power Q whole by Q is there. So A is greater than or equal to 0, B is greater than or equal to 0. Say this is the second equation. So with this inequality, A power P equal to B power Q, when both are equal is here, then automatically given this condition, first condition is obvious. Okay. Here the first equation is obvious for the integral x. But this is the first condition. Given the statement is first equation and the product of AB is the second equation. So when from the first equation is obvious, by individual integrals are is an equivalent to 0. Okay. So our assumption, if it is not equal to 0, suppose we are integrable, the different integrals are when it is 0, then directly theorem is obvious. Suppose when it is not equal to 0, so product of the functions, measure functions is measurable, and substituting, suppose this value is mod f of x by integral mod f whole power p and whole power 1 by p with measure b equal to mod g of x by integral mod g whole power q of the measure and whole power 1 by q. So we are taking the values is a and b is there. After the substitution, say that is the second one. So product of those equations, a into b means mod, these values are substituting in the second equation, mod f of x into g of x by integral mod f whole power p d mu and whole power 1 by p, integral mod g whole power q d mu and whole power 1 by q less than or equal to. So the product of 1 by p of this one plus 1 by q of this one. Say that is the third equation. After the simplification, we are getting the integrating the inequality on both sides, we are getting integral x mod fg on arbitrary measure, throughout the arbitrary measure mod fg d mu less than or equal to integral mod f whole power p d mu whole power 1 by p, and enter this values and equal. After the cross multiplication, we are getting the given the result for Holder inequality for integrals. See, this is the one of the important theorem. Okay, students. Okay. Any doubt? If you have any doubt, please contact my number, because this is the 1.5 hour session. So, if you have any doubt, please, if you have any doubt, as an personally throughout WhatsApp for subject purpose, please note down my number 9989476833. This is my number. If you have any doubt, please contact as an personally through WhatsApp. For subject point of view, don't deviate here. In each and every session must important for your purpose. Okay. Now this is online session, very useful. Enter the concept of functional analysis, whatever it is. Any paper is there. But in now as an personally, now my paper is functional analysis. That's why I am talking here. Okay. That's why just I give the one of the expressions and some other notations and explained throughout the online session. Okay. Now, this is from the beginning of linear space, we have explained the concept, some other examples, and one of the inequality, Holder inequality. There are three types of inequalities is there for sets, sequences, and throughout the integrals. Now, there are three types of Holder inequality is there. Now, according to the Holder inequality on for the sets, now replacing the p and q by 2, we are getting the Cauchy-Squarge inequality. Now, this is very useful from the beginning of first question is given. State and prove Holder inequality or define linear space. Give example as and briefly. Okay. Now, there are two questions and after the explanation on this minute here. Okay. Now, see this Minkowski inequality. Please stay on the line. Please stay on the line. Okay. Please stay on the line. Students, this is one of the important inequality 1.4.4. Suppose you are referred in the previous papers, almost all those previous papers just you have to download through the university website. Okay. Now, those papers in the functional analysis, now those from the beginning of the essay question is very important. Now you must attempt 4 essays. Already one essay is there. Number of times is given. State and prove Holder and Minkowski inequality. Okay, and state and prove Cauchy-Squarge inequality. Define linear space. Give example is on briefly. Okay, now these are all questions. And till this minute, okay, now that is the explained the concept. From the explained the concept of the how to given the questions. Okay, now see this one 1.4.4. This theorem is very important in the final examination. Now Minkowski inequality. Okay, P is greater than or equal to 1. Suppose if P is greater than or equal to 1, then summation mod xi Minkowski with respect to the addition is there. Summation mod xi plus yi whole power p and whole power 1 by p is less than or equal to summation mod xi whole power p and whole power 1 by p plus summation mod yi whole power p and whole power 1 by p is there. So xi yi values are complex numbers. Okay. Now this is in between addition. We are taking the addition is there. Please rectify this one. In between addition is there. Okay. In the first one, Minkowski inequality statement, summation mod xi plus yi whole power p and whole power 1 by p. This theorem by using a triangle inequality is there. Okay. In an inner product space. Okay. That is the already this is maybe 9th unit. Summation mod xi whole power plus yi whole power p and whole power 1 by p less than or equal to summation mod xi whole power p and whole power 1 by p plus summation mod yi whole power p and whole power 1 by p. Now there are two complex numbers here. Xi values and yi values are complex numbers. Okay. Say this is the, from the given the statement is first equation. In this inequality, it follows that we are substituting here p equal to 1. We are getting the expression is summation mod xi plus yi. Here I varies from 1 to n. Now it cannot exceed. It cannot exceed means that is the less than or equal to. Okay. Summation mod xi plus summation mod yi. So from the first equation, in this equation, first equation, it holds good. In the, for the substitution of p equal to 1. Suppose case 2 is there. Case 2 is there. P is greater than 1 is there. So since mod xi plus yi is less than or equal to summation mod xi plus summation mod yi. Now after the condition, we are in the replacing of by p, summation mod xi plus yi be greater than 1 means we are given the equation is whole power p and whole power 1 by p less than or equal to summation. Now mod xi plus yi can also be written as individual of the module of the summation means the summation of the modules. So summation mod xi plus mod yi whole power p and whole power 1 by p is there. Say that is the individual sums. Okay. Modulus of the individual sums. Say that is the second equation. So we are replacing mod xi plus mod yi whole power p minus 1. Mod xi whole power p can also be written as whole power p minus 1 plus 1. And at the same time, this value can also be written as p minus 1 and plus 1 is there. We are getting the p value is there. So mod xi plus yi whole power p can also be written as, so whole power p means p minus 1 plus 1. Now after the simplification, mod xi plus mod yi whole power p minus 1 into plus 1 means as mod xi plus mod yi. So now this is the, after the distribution here, we are getting a mod xi plus mod yi whole power p minus 1 into mod xi. Mod xi plus mod yi whole power p minus 1 into mod yi. Now we are getting the, after the, we are taking on both sides at the summation mod xi plus yi whole power p again. Left hand side part can also be written as p minus 1 plus 1. So p minus 1 into mod xi less than or equal to summation mod xi whole power p and whole power 1 by p. Summation mod xi plus yi whole power p minus 1. So, and whole power 1 by q is there. Okay. So that can also be written as summation mod xi whole power p and whole power 1 by p, summation mod xi into plus mod yi whole power p minus 1 whole power 1 by q, means p by q minus 1 by q. Okay. Now this can also be written as p into 1 by q means p by q minus 1 by q is there. So whatever it is. So 1 by q is also same. Now after the simplification we are getting, so that value is, what is that? Now we are taking the value p minus 1 means p into whole power minus 1. Okay. Now here mod xi means, now this value can also be written as mod xi means again mod xi whole power p and whole power 1 by p. So mod xi can also be written as whole power p and whole power 1 by p. Summation mod xi plus yi and whole power p minus 1 or p minus 1 means p. So and another value converting into this side. Okay. So finally we are getting same times. So in terms of yi, we are taking the in terms of yi. In terms of yi, and the above part is in terms of xi. So after the simplification, summation mod xi plus yi whole power p into summation mod xi whole power p and whole power 1 by p plus summation mod yi whole power p and whole power 1 by p of summation mod xi plus mod yi whole power p and whole power 1 by q is there. Okay. Now dividing throughout by this one. Dividing throughout by this one, we are getting summation mod xi plus mod yi whole power p, and p can also be written as 1 minus 1 by q less than or equal to summation mod xi whole power p and whole power 1 by plus summation mod yi whole power p and whole power 1 by p. So 1 minus 1 by q can also be written as 1 by p is there. From the condition of 1 by p plus 1 by q equal to 1. So this condition 1 minus 1 by q means 1 by p is there. Okay. So we are getting the result. That is the first equation. So that is Minkowski inequality. Please rectify, given the statement in between the addition is there. But in the above statement, addition is not there. Okay. Now that is the Minkowski inequality. Some students are, now that is the entire the concept is by that is the by heart. Okay. After the by heart, now represent as the same notion. Okay. In between the addition is there. Please note down. In between the addition is there. Okay. Please practice. You must practice throughout the according to the subject. Okay. Now that is the proof of Minkowski inequality for sets, and for sequences means we are in the replacing x and y by any two sequences x and yn. Now those sequences p lies between 1 to infinite throughout the scalars, either real numbers or complex numbers. Summation mod xi whole power p less than infinitive, summation mod yi whole power p less than infinitive. Okay. Now the term is also referred in the same manner, replacing x and y by xn, yn sequences. That is the simplest proof. Okay. Please note down. So that is also rectified here. What is that? This is y, not z is there. Okay. That is the simple proof for sequences. So for integrals means we are applying on both sides integrals. X be the set of all measures. Okay. Arbitrary measure is denoted by x, and that arbitrary measure we are taking in any two functions, f and g be any two the set of all measurable space. Any two functions in a measurable space, f and g. So replacing x and y by f and g. Now in the above theorem, we are getting the Minkowski inequality for integrals. That is also a very simplest theorem in the final examination. Okay. This is also very simple. Please practice all the proof of Holder inequalities and Minkowski inequality. Now, tomorrow we will discuss the definition of normal linear space according to the before that the concept of linear space and examples and some other inequalities, Minkowski inequality, Holder inequality, and Minkowski inequality. There are three types of proofs here. Holder inequality, there are three types, and Minkowski inequality, three types for sequences, for integrals, and actual concept is on throughout the linear space of the part. Now, from the definition of the above concept, we will learn tomorrow we will discuss the normal linear space. That is the simple short form as NLS. NLS means normal linear space. Tomorrow we will discuss the normal linear space definition, examples, and some other theorems and problems. Okay, students, if you have any doubt here, please respond. If you have any doubt for this subject, that is the functional analysis paper, especially in this session, you must contact through my number. Please note down 9989476833. This is my number and WhatsApp number. Please contact us personally for the subject point of view, and I must rectify your doubts. There is no problem. Okay, once again, thank you one and all. Tomorrow we will meet again, same timings. Okay, same class. Thank you one and all. Wish you all the best and wish you good luck.